So if we read this question here, we've got a binary coded shaft encoder disc which is attached to a weather vane. As the wind blows on the weather vane, it turns the weather vane round to indicate the wind direction. So this is attached to a shaft here, so you can imagine the weather vane attached there, so as the wind blows on it, it's going to turn it around like that. And it's a 3-bit binary coded shaft encoder, and it's been partially completed. So if it's 3 bits, with 3 bits you're going to have from 000 to 111, aren't you, which is from 0 to 7. So you've got 8 different possible values. So we need 8 sectors on the disc. So we're going to need the outer ring here. Now if we do that, we've only got 4, so we need to subdivide again in order to get 8. So just subdivide again like that. You'll be able to use a ruler. So we need an output from 000 to 111. So usually you would have 000 here, and as you work your way around, you'd count in binary. So you'd have 1, 2, 3, 4, 5, 6, 7, and we're going to be able to do that here. So we'll have 0, 0, 0. Just remember that the most significant bits in the centre there, and in the centre ring, and the least significant bits in the outer ring. So we're going to have 0, 0, 0 there. We're going to have 0, 0, 1 here. So that's the least significant bit, so we need to shade this part here. And then we've got 2. So we're sort of working our way around there. 0, 1, 2. So there's 0, 1, 0, which is 2. Then for 3 we need 0, 1, 1. Remember, that's the outer ring there. So that's 3, 0, 1, 1. Then we need 4, which is that one there. So remember, that's the most significant bit. 1, 0, 0, 1, 0, 0. Then for 5, look like that. Then for 6, so we've already got, look, 4 plus 2 plus 0 is 6, 1, 1, 0. And then we need 1, 1, 1. Like that. So that's a 3-bit binary coded shaft encoder disc. It's not a grey code disc, so we're not trying to make 1 bit change at a time. It's a binary coded shaft encoder, so you need to effectively count in binary as you go around there. So that's worth 2 marks. It tells you below that the binary value that it asks you to circle the binary value that represents southwest if north is represented by 0, 0, 0. So this represents north there. So we're going to have south here, aren't we, opposite north. We're going to have east here, west up there. So that's going to be northeast. That's going to be southeast. We've got southwest over there, and we've got northwest up there. So southwest would be 1, 0, 1 there, like that. The significance of that little 2, by the way, just shows that it's in binary. If you wrote 101 like that, you could put 10 there to show that's in base 10. So that would be the numbers of 1s, that would be the numbers of 10s, and that would be the number of hundreds. So you're in base 10 because every time you move along to the next digit, it's showing you how many. You're moving up in multiples of 10. So just that's the significance of that 2, if you weren't sure what that 2 was. Of course, what you've got here, you'd have 3 infrared LEDs in a row. So if you have the disc in this orientation there with the axle there, for each ring would have its own infrared LED there. and on the other side you have the photodiode, wouldn't you? On the other side there, like that. So remember, these things are called bands. That's a band, that's a band, that's a band. So if the band was transparent, then light would be able to pass through from the LED to get to the photodiode. And if the band wasn't transparent, if it was opaque, then light wouldn't be able to get through, would it? So the binary shaft encoder disc has an infrared LED placed above each ring, and the infrared photodiode below each ring in line with the LED. It's able to pass through the unshaded sections, but is blocked by the shaded sections. This shows the circuit to drive the infrared LED. The infrared LED's got a forward voltage of 1.2 volts. So if you imagine a little voltmeter there, the drop across there is 1.2 volts. So the drop across there must be 5 minus 1.2, which would be 3.8 volts. It gives us the maximum LED current, 15 milliamps. Calculate a suitable value for R. So R equals V over I. You've got to be careful here. You want the resistance of the resistor, so you must use the voltage across the resistor, not 1.2. You can't say the resistance of the resistor is equal to the voltage across the LED divided by the current. The resistance of the resistor is the voltage across the resistor. You've got to be careful there. Divided by 15 milliamps, which is 15 times 10 to the minus 3. I mean, the easiest way to put that in your calculator is just leave it as 15 times 10 to the minus 3. So then you can just go onto your calculator there. 3.8 divided by 15, that button means times 10 to the minus. So, sorry, that button means times 10, and then minus 3 there equals 253. Excuse me. 253 ohms. You can't necessarily, well, you can't buy exactly a 253 ohm resistor. Remember, on our syllabus you have to select a value from the E24 series. If you look at the data sheet, they'll tell you that the next one up in the E24 series is, you always choose the next one up, don't you, for protective resistors. The next one up is 270, so you must, for the full 3 marks, choose the 270 ohm resistor. So over the page, we've got a question here which shows the actual infrared photodiode receiving circuit, and it's connected in to a NOT gate, and it tells you photodiodes have a reverse current. Remember, it's in reverse bias. A large current when illuminated, when it's light, and effectively no current in the dark. Now, if you just have a little think about this circuit here, what's the voltage going to be at the input to the NOT gate in the light and the dark? Well, voltage across the resistor is V equals IR, isn't it? So in the light, the current's relatively high, so you've got relatively high current, which means the voltage across the resistor is going to be relatively high. So if we call this point X here, look, so in the light, the voltage across the resistor is high, so there's going to be a relatively high voltage drop across there, so the voltage at X is going to be low. So V out is going to be high, because it's a NOT gate. Similarly, in the dark, there's no current through here. Current zero, so the voltage across the resistor is 0, so there's no voltage drop. So the voltage at X, if there's no voltage drop, the voltage at X is going to be 5. So in the dark, the voltage at X is going to be 5. That's a high, so V out is going to be low. So in the dark, the output voltage is going to be low. It's definitely going to be low, isn't it? Because if the input voltage is 5, it's a NOT gate, the output voltage is definitely going to be low. But if you're going to detect a difference in the light, if you want the output voltage to be high, excuse me, you need the input voltage to be low. But how low? How low for a NOT gate? How low does low have to be in order for the output to be high? Well, if you imagine the input for a NOT gate, you could imagine sort of a cut-off point maybe at 2.5 volts like that. So if this is sort of V in, this graph here could be from this bar here from 0 to 5 volts. If the input voltage is high in this region here, then the output is going to be low, and if the input voltage is low, then output is going to be high. So anywhere below excuse me, for an input voltage anywhere below 2.5, you'll get a high output. So we need to select the right resistor value here, so that when the voltage here, we're going to assume 2.5 is our cutoff point. If it's just sort of if it's exactly say at 2.5, let's say we're going to get a high out. So state any assumptions made. So if Vin is lower or equal to 2.5 volts, this is for the NOT gate. For the NOT gate, then V out high. So and we want this to happen in the light, don't we? In light conditions. In light conditions, we've said we're going to get a high out. So let's have a think. What would we need to do to make that exactly 2.5, and just to be on the cusp here of in light conditions giving us a high out? So 2.5 there. Well, the voltage across the resistor would be 2.5, wouldn't it? So if we look at V equals IR, and we've got R equals V over I, our V is not 5, it's 2.5. 2.5 divided by 5 micro, and if you put that in your calculator, you'll see that's 500,000 ohms, or 500 kilo ohms. So a bit more of a challenging question, that one. Next one, when the wind direction changes from north to northwest, it indicates southwest for a moment before going north. So let's have a look. What's it done? It's gone from northwest to north. So if your weather vane's here like that, and then it gets blown from northwest to north, it's going to move straight from northwest to north. It's not going to sort of go through one position and then swing round to north. It's a sort of a fake reading. So going from northwest to north, it's gone via southwest. So let's have a look. Northwest to north. So if we go back, here's northwest there, and it should have changed to north. So that's a case of 111 should change as the as this disc here, this part of the disc here, spins round to there. These three block the light, don't they? And if all of these were in a perfect line there, all of the edges of the bands were in a perfect line, then as this rotates round, light would suddenly pass through all three of these, wouldn't it? So we should be going straight from 111 to 000, but it's giving a reading as if it's going via southwest. So instead of going straight from 111 to 000, it's going via 010. Now that suggests that this one changes first, wouldn't it? It's gone to 0 first in the middle for some reason. Now it could be that protrudes slightly, the edge of that band protrudes into there. So the edges of the bands might not be aligned, or the three photodiodes, if you imagine the three photodiodes, 1, 2, 3, if they weren't aligned and one of them was just protruding into there a little bit in that direction, if it was sort of, instead of being 1, 2, 3, one of them was here, that might change first. So the problem is the three edges of the bands, or the three LEDs, we don't know which, aren't perfectly aligned. The middle band, or the middle LED, is misaligned with the other two. So that's the problem. So going back over the page there, suggest one likely reason for this error. The one likely reason would be that either the edges of the bands or the LEDs aren't aligned, and specifically it's the middle one that's not aligned with the others. The last question is, what change could be made to the encoding disk to eliminate this problem? Can you remember the grey code disk? Only one of the bands changes physically on the disk at a time. Instead of counting in sequence in binary, it doesn't. It sort of jumps around, and it's possible to get all 8 values where only 1 bit changes at a time. Now it's asked you what change could be made to the disk, so I would be expecting you'd physically have to talk about what's going on physically on the disk, and say only 1 band on the disk changes at a time, and that is a grey code disk. If you look at the mark scheme, if we just come over to the mark scheme there, they've been a little bit generous. You don't have to necessarily say the grey coded disk. You can, for 1 mark, use a grey coded disk. It accepts a suitable description of a grey coded disk. Now if you say only 1 bit changes at a time, is that sufficient? It hasn't been in previous years, but you do get inconsistencies sometimes between different years. I would say a suitable description would say only 1 band changes at a time. So you have to talk about the physical description of the disk rather than just 1 bit changes at a time. Although I think in some years that may be acceptable, so you just need to be a little bit careful there. Question 2, you've got an analog to digital converter. The analog input voltage is here. It's the analog input voltage. So what happens, we've got a start signal that will go to the microcontroller. The microcontroller is actually counting, so there'd be a port here where you increment the value. So you've got a binary value coming out of here which is counting. So you've got your binary value there, binary value which is counting up. So it'd be, if it was an 8-bit output, it'd be all zeros, and then it'd count to, in binary, 1, 2, 3, 4, so on and so on. So that's input into the DAC, remember, which is based on a summing amp. So as this increments over time, what's going to happen is over time there, the DAC output voltage is going to ramp up, isn't it, in small steps. Every time it counts up 1, the DAC output voltage is going to increase, and the input voltage would be some value up here. So what's going to happen is the comparator is going to compare this value here. There'd have to be a -1 inverter in there to turn the negative value from the summing amp into a positive value as well. So this would compare these two here, and the microcontroller would be polling the output of the comparator. So when this value from here is lower than the analog value, the microcontroller would detect that output value from the comparator, and it would keep counting until eventually, as soon as the DAC output, the binary, this is an analog output from here. This is binary, but this turns it into a varying analog. So as soon as that analog value exceeds the analog input voltage, then the comparator output will change. The microcontroller will detect that, and it will stop counting. Now at that point, the end of conversion signal would change here, and there'd be a system up here detecting that the conversion had finished. Now if you wanted to take that output and use it somewhere else, what you'd do is you'd wait until the end of conversion signal had changed. Usually that would go high, and then you've got a latch here, and if the latch is enabled, the output, the binary value here, could be put into the latch and latched over here. So if you had, I don't know, 0xB3 for example, as your binary value, so you've converted your analog into digital, as soon as you've latched, that value there would be held there, 0xB3, and if you enabled your tri-state buffer, the output would match the input, and you could then save that value or write that value somewhere else. So what's the question? The op amp is used for a comparator. This is sort of a standard question. It's due to the large differential voltage gain. The fact that the comparator consists of an op amp with a large voltage gain. It's not acting as an amplifier, but it does internally have a large voltage gain, an open loop gain. It's a tiny difference between the inputs or saturate the outputs. So that's why that's the feature that makes it a good comparator, a large differential voltage gain. Now it tells you down here, the DAC does have an 8-bit input value, and gives an output voltage of 5 volts for an input value of 0x80. So for example, when the microcontroller is counted to 0x80, the DAC voltage out here is 5 volts. So 5 volts is equivalent to an input of 0x, I suppose we could use 3. 5 volts is equivalent to that input there. So it's asking us to show that we would get 7.1 volts out when the input's B6. Well, all you've got to do here is convert that into a normal sort of denary number. In binary, that would be 1 0 0 0 0 0 0 0, wouldn't it? That's your 8 there, 0 there. So remember, once you've got the full binary there, that's the number of 1s, 2s, 4, 8, 16, 32, 64, 128. So in normal denary, that's 128. So what we're saying is, we get 5 volts out with sort of a denary input of 128. So we're trying to show we should get 7.1 volts out when we put B6 in. Well, if we work B6 out in binary, remember it's 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So 9 is 9, 10 is A, 11 is B. So to get 11 you need 8 and a 2 and a 1. So remember, if you're thinking of that as a 4-bit number, 8 plus 2 plus 1 is 11, and a 6 would be a 4 and a 2. But now we've expanded that out now to an 8-bit number. So you've got 1, 2, 4, 8, 16, 32, 64, 128. So what we've got there is 128 plus 32 plus 16 plus 4 plus 2. So that's 130, 162, 172, 178, 182. So 128 gives us 5 volts. We need to show that 182 should give us 7.1. Well, there's different ways of doing this. If you wanted to, you could work out if 128 gives you 5 volts, what should an input of 1 give you? Well, if you do 5 divided by 128, 5 divided by 128 gives us 0.04. So a count of 1 is 0.04 volts. We've got 182, so times that up by 182 there, and we get 7.1 volts, which is what we were trying to show. So we've done it. Might be slightly quicker if you're trying to show 182 gives 7.1, just as ratios, work out how many times that is bigger than that, and then times it by that. So over the page, we've got the output from the comparator is connected to D0 of port A, and the latch enable input is connected to D4. So the output from the comparator is connected to D0 of port A on the microcontroller, and it tells you that the enable input of the latch is connected to D4. So the enable input of the latch is connected to D4. So from the perspective of the microcontroller, D0 is an input and D4 is an output. So back over the page again. It says write the assembly instructions to set D0 to D3 as inputs. So when it says 2, that means inclusive. So we want D0, D1, D2. Well, actually, let's write this the other way around, because normally you put the least significant bit on the right hand side. So D0, D1, D2, D3. We want all of those to be inputs. And D4, 5, 6, 7 we want to be outputs. So we'd have D4, 5, 6, 7. We want all of those to be outputs. And this is port A we're talking about. Well, can you remember there's sort of a mirror register called tris A, and the values you put in tris A determine whether each of these individual bits on port A are inputs and outputs. And can you remember 0 sort of looks a bit like O for output, 1 looks a bit like I for input. So in here we put 0, 0, 0, 0 because we want out, 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 out. And in here we put 1, 1, 1, 1, 1 there. Just got to the point where we needed this value in the register tris A to determine which of the bits on port A are inputs and outputs. So that in hexadecimal is nor F, isn't it? Nor X, nor F. So all you need to do is move that value into this register here. So anytime you try and move something into a register, first you have to move it into the working register, mov into the working register, and then say which value it is you want to move into the working register. And then you want to move it from the working register into a register. Which register? Tris A. So that's how you would configure port A as requested. Next one along, in operation, the microcontroller sends bytes to the DAC. The comparator compares the input voltage with the output voltage from the DAC. When the output of the comparator changes, the microcontroller stores the byte in the latch using the enable line. Explain why the latch is needed. So let's just turn over and have a look at the diagram here. What would happen without the latch if you just took this binary value straight from here and almost, passed it straight through to the output if you didn't have the latch there? Well, as the microcontroller is counting to create this ramp, this value here is changing all the time, isn't it? From 0, 0, 0, 0, 0 to 0, 0, 0, 0, 1 and so on. So the value that you'd have from the output of the microcontroller is changing all the time. So that's why when you have the latch. When the process is complete, it latches that value there and it holds it there, holds it steady there. So you could almost start a new conversion over here. If you get a new input, if the input changes, you could start a new conversion while the previous analog to digital conversion would be held constant there. So if there was a slight delay before you needed it over here, it'd be fine, you'd have it held constant there. So if you look at the mark scheme, you'll see those 2 points there on the mark scheme. You're asked, it mentions the output of the latch is connected to a tri-state buffer. State the function of the tri-state buffer. Question 3, system diagram for a type of ADC, similar to question 2. In operation, the microcontroller sends bytes to the DAC, so that's this way here. The comparator up here compares the input voltage here with the output voltage from the DAC. When that does change, because this is increasing, as discussed in question 2, when the output of the comparator changes, the microcontroller stores the byte in the latch using the enable line. So the bytes go into the DAC, but it can also come around this way into here. So using this pin here, the data can get latched at the output there of the latch. The output from the comparator is connected to D0 of port A of the microcontroller, and the enable input of the latch is connected to D4 here, port A. So I've just added those on the diagram there just to help sort of try and understand what's going on. Port B is connected to the DAC there, and also to the latch. Now it's given that introductory information, but this is almost a little standalone question here. So 3A, to check the output state of the comparator there, the microcontroller needs to be able to store the value of port A in the working register, isolate bit 0 of the working register, and check if the working register is 0, and it asks to write assembler instructions for this process. So don't forget, it's port A. These two are connected to port A. It's port B that's connected around here. So if we just have a look at some notes I've made over here, the first thing you need to do is store the value of port B in the working register. So that's just this command here. If you remember, you've got the data sheet with the commands on. Mov means move, and in English you read from right to left, don't you? So move the contents of a register into the working register. So you're moving the contents of a particular register into the working register, and then it's after that command you say which register it is you want to move the contents of into the working register. So it's port A. So that's the first command you need. So that's worth 1 mark. It then asks you to isolate bit 0 of the working register, and that's this line here for 1 mark. And then check if the working register is 0. You have to use the JPZ command, 1 mark for noting that. But whenever you use that, you would also need a label to go with it. And I've called my label out, but you could have called it anything. So how does that work? Well, just to give you a reminder then of the process, let's say port A is an 8-bit port with these particular values in, so we don't know what values they'd be, but I've just written D0, D1, 2, 3, 4, 5, 6, 7. Remember, this is bit 0, bit 1, 2, 3, 4, 5, 6, 7. So the first thing you would do is move the contents. There's the contents of port A. You would move those contents into the working register. So as a result of that first command there, the working register would now have exactly the same data in as port A had in there. So that's what I'm trying to show with the second line there. Now, with that AND W command, what you're saying is you're going to AND the contents of the working register with 0x01. So I've written that here. We're going to AND the contents of the working register with 0x01. Now, in the working register, we don't know exactly what's, whether that's a 1 or a 0, but we've got this data. So if you write out 0x01 in binary, we're going to get this, aren't we? So what you're going to do is AND this with the contents there of the working register. That means ANDing this with this, and ANDing this with this, and ANDing this with this, and so on. Now, if you think about the AND gate, the truth table, whenever you AND with a 0, doesn't matter if that's a 1 or a 0, does it? If you're going to AND with a 0, you'll get a 0. So ANDing these two together, 0, 0, and so on. Now, this one here, we don't know if D0 is high or low. That might be high, or it might be low. Well, if it was a high, 1 and 1 is 1. If it was a low, if D0 was a low, you get 0 and 1, 0. So you're going to get the same thing, aren't you, as a result of the AND command. If it's a 0, 0 and 1 is a 0. if it's a 1, 1 and 1 is a 1. So you're going to get exactly the same thing as a product of that operation. You're going to get D0. So the working register is going to contain 0, 0, 0, 0, 0, 0, 0, D0, which may be high or low. So we've got two scenarios now. If D0 was low, then the working register would be all zeros. And when the working register is all zeros, do you remember there's the Z flag, the 0 flag? And that will go high. That only goes high when the working register is all zeros. And if the Z flag is high, the JPZ command will jump. So in this case, we'd have, further down in the program, we'd have a label out, and that would jump to the label out, and it would leave this loop. You would normally have underneath there, you might have a loop label, and just JMP loop. So perhaps it would be going permanently around there. Opposite to that, if that was high, you'd have 1 and 1 was a 1. So if D0 was a 1, then you'd have a 1 there, wouldn't you? And the working register would not be all zeros. The Z flag would stay low, so JPZ wouldn't jump. It doesn't jump, it only jumps if the Z flag's high, if you've got all zeros. So that answers our question. The question was 3 parts. Store the value of port A in the working register. Sorry, I'm looking at the wrong one here. 3A, store the value of port A in the working register. Isolate bit 0 of the working register and check if the working register is 0. So just to remind you, whenever you see isolate bit 0 of a particular register, that means using the AND-W command, and you place the 1 in whichever bit it is that you're trying to isolate. So if you were trying to isolate this bit here, then you'd place the 1 there, and you'd have 1, 0, 0, 0. So in hexadecimal you'd have 0, 8. You'd have 0x, 0, 8. So that's question 3A. Question 3B is this question here. Write the assembler instructions to store the value of port B in the working register. Set bit 3. Set means set it high. Clear, if you ever see the word clear, that means make it low. So set bit 3 of the working register without changing the value of any other bit, and then store the value of the working register back in port B. Most people were okay with 2 out of the 3 there. If you look on the mark scheme, the first command is moving the contents of port B into the working register. The last command is moving the contents of the working register back to port B. So most people are happy with the first and the third, but what about that middle one? It's got OR W there, 0x, 0.8. So that's the command corresponding to this one. That's set bit 3 of the working register without changing the value of any other bit. So let's have a look at how that is achieved. So we've got, similar to the previous page, if we write out, there's the contents of port B. We don't know if any of these are high or low. We've moved the contents of port B into the working register there. Now what would happen if we ORed the contents of the Mr. W out there? What would happen if we ORed the contents of the working register with 0x, 0.8? So there's 0x, 0.8, there's the 0, there's the 8. So if we did this here, if we took D7 and ORed it with 0, what would we get? Well, there's the truth table for the OR gate. So we're ORing with a 0. Now a 0 ORed with a 0 is a 0, and a 1, sorry, I think I've written this truth table out incorrectly. That was silly. Let me just change that there. So where were we? We were looking at what would happen here. We're ORing with a 0. So 0 OR 0 is a 0, but 1 OR 0 is a 1. So I've written this down over here. Look, 0 OR 0 is 0, 1 OR 0 is 1. So actually, if you're ORing with any bit with a 0 here, it doesn't change its value, does it? A 0 will stay as a 0, and a 1 will stay as a 1. So it doesn't matter if that's a 1 or a 0, we're going to end up with the same thing. So we can write D7 down here. The end result will be D7. And that's similar to all these other ones there. Anytime you OR with a 0, you're not going to change the value. So these all stay the same. So what about if you OR with a 1? Well, if you look at the truth table, 0 or 1 is a 1, so that's become the opposite, hasn't it? Well, it's become the opposite, but the most important thing is it's gone high, isn't it? 0 or 1 is a 1. 1 and a 1 is also high. So when you OR with a 1, you'll get a high regardless of whether you've got a 0 or a 1. You can see that here, can't you? 0 or 1 is a 1, 1 or 1 is a 1. So you've not changed, that's not correct. I was going to say you've not changed the bit you have in this case, and you haven't in this case, but the main thing is that they're both high, aren't they? Regardless of whether D3 is a 0 or a 1. So I've underlined that there, look, this is the important part there, that's going to become a 1. So we haven't changed the value of any of these bits, but we have definitely made sure that D3 is set high. And that was the question we were given. If you remember, the question was set bit 3 of the working register without changing the value of any other bit. Now, would it have been possible to use other commands? Did you have to use the OR command? Well, you can't use the AND command, because if you think about the AND command, if you've moved the value of port B into the working register, and you've got all these bits here, if you AND with 0x08, anytime you AND with a 0, you're definitely going to get a 0, aren't you? If that was a 0, 0 and 0 would give you a 0. If that was a 1, 1 and 0 would give you a 0. So that potentially that might change the value of that bit. If that bit was 1 there, and then you've ANDed with 0 to get 0, you'll have changed the value of that bit, wouldn't you? So that's what I've written here. The D7 to D4 and D2 to D0 will be set to 0 regardless of their value, which is not what we want. So that you wouldn't be able to use that. D3 would be also D3 would be unchanged. If it was a 1 and a 1, it would give us a 1. A 0 and a 1 would give us a 0. So D3 would be unchanged. And remember, we were supposed to set bit 3 high, not leave it unchanged. So you can't use I missed the W there again. You can't use the AND W command for two reasons. One, it sets all the other bits to 0 and it leaves D3 unchanged. For similar reasons, you can't use the XOR command either. I'll leave that as an exercise for you to consider. So just with a little bit of thought, thinking out sort of the truth tables, and maybe using this kind of approach if you have time, will just help you with this kind of question. So that was 3B. Just turning over the page then, we're on to 3C. Explain what is meant by the term active low. Well, if we just read the preceding part, when the conversion is complete, the byte stored in port B needs to be stored in the latch. So what we're saying is the byte stored here needs to be stored inside the latch and put at the output of the latch, and that involves the latch enable there. So over the page, the enable input of the latch is active low and needs to receive a single pulse to store the data. So what does active low mean? Well, there's slightly different ways you might phrase it, but if you look at the mark scheme there, if something is active low, the input needs to go to logic 0 for the process to initiate, or for the input to be active. You might phrase that in slightly different ways, but the first part is fairly straightforward. If something's active low, it needs to go to logic 0. It needs to go low voltage, needs to go to 0 volts. That's the kind of detail you need. and then it's just wording that second part. What will happen when the logic goes to 0? Something's going to initiate, the process will start, something along those lines. It then says, draw in the space below a diagram. I just lost the focus there for a second, sorry about that. Might just have to move back there. Draw in the space below a diagram of the signal that must be sent by the microcontroller to the enable input of the latch. Well, it's active low, so normally it would be high. It's going to go low. Normally you would go low temporarily, wouldn't you, to initiate a process, and then you'd return to high again. You wouldn't want to leave it at low, because that might re-trigger the process multiple times. You only want to trigger the process once. It did say label the logic levels, so we've got logic 1 there, logic 1 over here again, and logic 0. So if you understood what it was looking for, that was a fairly straightforward one there. Okay, the last one then. We have 2 marks. There's the assembler code to create the pulse. Look, the assembler code to send this pulse is given below. Calculate the duration of the pulse if the clock frequency is 1 megahertz. So you've got a frequency there, so time period is 1 over frequency, 1 over 1 mega, if you put that in your calculator, or just if you know a mega is a million, 1 divided by a million is a millionth, and that's 1 microsecond. That's 1 times 10 to the 6, sorry, minus 6 seconds, which is 1 microsecond. Now that means the time period for 1 clock pulse is 1 microsecond. So now if you look on the data sheet, each of these take 1 clock pulse. So you've got 1, 2, 3, 4, 5, 6 clocks there. A lot of students think at that point, well, I've got my answer then. I've got 6 commands. 6 times 1 microsecond gives me 6 microseconds. But if you just think a little bit about what's happening with those commands, then there's a little bit more to it than meets the eye. So over to this piece of paper here. If you just consider what these are actually doing, and it does take a little bit of thought, but it might just get you the extra mark that you wouldn't otherwise have got. So MOV RW port A is going to take the value of port A, move into the working register. So there's port A. When you execute that command, it moves that the value there into the working register. Then you've got AND W nor X EF. So there's E and there's F. So what's going to happen when you AND the contents of the working register there with this? Well, if you think about the AND command, if that's a 1 and a 1, you're going to get a 1. If it's a 0 and a 1, you're going to get a 0. So this one remain unchanged. A 0 and a 0 give you a 0, a 1 and a 0 give you a 0. So you're always going to get, as a result of that AND operation here, you're always going to get a 0. So these here will remain unchanged there. And these remain unchanged there. And like we said a second ago, D4 in this case has been set low. Now that accounts for these 3 commands here, because we moved the contents of port A into the working register, we've ANDed, that's the product there, and then we've moved that back into port A. So to make it low, to make D4 low, that's 3 clock cycles. 1, 2, 3. Now what do the next 3 do? Well, they're going to move the value port A there back into the working register. So it'll have been moved back into the working register again. This time you've got OR W nor X10. So let's write that out. Bum, 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 bum. What happens when you OR with a 0? A 0 and a 0 give you a 0. A 1 and a 0 give you a 1. So these are going to remain unchanged there, just like before. And what's going to happen to our D4? Well, our D4 was 0. and now we're ORing with a 1, so we're going to get a 1, so it's gone to high. And move that back into port A, and these 3 have remained unchanged, those 4 have remained unchanged, and we've got a high. So the first 3 are making D4 low, and the next 3 are making D4 high. So the question that was asked here was calculate the duration of the pulse. Now, what do we mean by pulse? It's a low pulse, isn't it? The pulse is this part. The pulse is the time that it's low for. So back in the code here, we've just said, haven't we, if we just have a look back over here, that the first 3 are basically creating the low pulse. So it's only the first 3 lines that we need to worry about. So it's 3 microseconds, because each clock is 1 microsecond, so we've got 3. So the answer for the last part is if you look at the mark scheme, is a pulse width of 3 microseconds. To take pictures, photographs of stars and galaxies, it's necessary for a telescope to track stars and galaxies in the night sky as the Earth rotates. This is often achieved by using a stepper motor to rotate the telescope. Compare the rotation of the armature, that's the part that rotates, compare the rotation of the armature of a stepper motor and that of a conventional motor when power is applied. Okay, a stepper motor is more accurate, but why is it? So for question 4a, what is it about a stepper motor? I don't think it's sufficient to say it moves in steps. You need to be a little bit more precise than that. It does move in steps, but those steps are fixed. They don't change each time. It doesn't move 1 degree one time and 2 degrees the next time. So you're looking to say a stepper motor turns through a specific or definite or certain angle, like a fixed angle, when the power is applied, when the current's applied. You're looking for a conventional motor doesn't. It turns continuously. It's the idea that it just keeps on rotating continuously, or it has inertia. So that's the 2 marks that you're looking for that. On to the next one. Explain why steppers are preferred for this application, because they are accurate, whereas conventional motors are not. Two common types of stepper motor are the unipolar and the bipolar. Describe the difference between the 2 types. They can both rotate clockwise and anti-clockwise. So what you're looking for really is to try and visualize the internal wiring of both. Unipolar, if you remember, have the center taps in the middle of the 2 coils, whereas the bipolar don't. The sequence of operation for both is the same: 1A, 2B, 1B, 2B. Sorry, I've written that down incorrectly, haven't I? It's 1A, 2A, 1B, 2B. Done the same thing over there. So the sequence of operation is the same. How do you, just coming into the unipolar there, how do you make the unipolar motors rotate? Well, you keep the center taps high on both of them, and normally 1A, 1B, 2A and 2B are all high. If you want to energize this coil, you'd make this end low, keep all the others high, and current would flow that way. So that's the first step in the sequence, 1A. Then to go to 2A, you'd make this high, and now both ends of these are high, so no current flows here. This is high, no current flows here. If you make this one high, current would now flow along here, and it would flow that way, and so on. Now if you take this coil here, current can flow that way if you make that end low, but it never flows the other way. You never make this high and this low. That's always fixed. The center taps are always fixed permanently high. So in a unipolar motor, current when it flows, only flows one way in a given coil. So it can only ever flow one way in that coil. Can only ever flow one way in that coil. That's in that direction. If you make that low, it can only ever flow one way in that coil and that coil. Now it's different for the bipolar. If you remember, the sequence of operation is 1A, 2A, 1B, 2A. Now, whereas for a unipolar, the sequence is a sequence of lows. So you make just that low, just that low, just that low, just that low. It's different for a bipolar. The sequence is a sequence of highs. So in the first step, you make 1A high, and you make the other end of the coil low. So just to say again, I've just made a correction here as well. Sorry, silly mistake on the table here. Let me just explain again then. For a bipolar motor, the sequence is a sequence of highs. So you make 1A high and 1B must be low. So step 1, 1A high, 1B low. The second step is 2A high. So step 2, you make 2A high, so you must make 2B low. Step 3, 1B is high, so you must make 1A low, the other end of the coil must be low. And step 4, 2B high and 2A low. So you can see here, if you're making 1A high and 1B low, current's going to flow that way. And then later in step 3, you've reversed the current direction, haven't you? You've made 1B high and 1A low, so you've reversed the current direction. So in a bipolar motor, current flows both ways. You have to reverse the current. Now, to reverse the current, remember, you can use an H-bridge. If you place each one of these in its own H-bridge, each stepper coil, the H-bridge is required for each coil to reverse the current direction. Here, what you would have is a single MOSFET required for each end of the coil. So if I just show you over the page here, for the unipolar motor, essentially for each coil there, you'd have the center tap at high, and this end here, to make it low, you'd have to turn on the MOSFET to connect it down to low. So those are the differences. Just returning back to the question. The question was, to summarise then, describe the differences for 3 marks. So you're looking for 3 differences. You could say current flows both ways in the coil for a bipolar, and current only flows one way in a unipolar. So that could be 1 mark, describing both. For a bipolar, it's the sequence 1A, 2A, 1B, 2B is a sequence of highs, whereas the same sequence 1A, 2A, 1B, 2B is a sequence of lows at the end of the coils. Or you could say no center tap in the bipolar, and coils do have a center tap in the unipolar. Or you could go into detail about the control circuitry. H-bridge required for each coil to reverse current direction, whereas a single MOSFET required for each coil connecting the end to ground. And that takes us on to the final question, which is final question. Unipolar stepper is used to rotate the telescope. The stepper motor is controlled by a microcontroller, which can only provide an output of 20 milliamps, but each stepper requires 1 amp. Draw a suitable driver circuit. So you want the MOSFET on there. So you could draw an N-channel MOSFET. You'd connect the gate there to the microcontroller there, and just connect these in here, and you connect that down to 0 volts there, and just draw the correct symbol for an N-channel MOSFET. And when this goes high at the gate there, it's going to turn the N-channel on, so current is going to flow down through the stepper coil, through the drain and out of the source there, down to 0 volts. and if you remember, anytime you've got a coil in a circuit, you need a protective diode across the coil, and the diode there needs to point in this direction here, in reverse bias. If it faced the other way, current would just bypass through the diode this way, and it would never flow through the coil. So you can check the mark scheme, but for the 4 marks, I think it's the correct circuit symbol for the MOSFET, correctly placed, and the diode in reverse bias, and you can check the mark scheme for the 4th mark. If you do, you'll see an attempt at a MOSFET gets you 1 mark, correct MOSFET gets you the 2nd mark, correctly connected 3rd mark, and correctly connected protection diode gets you the 4th. So 5A, we've got a general closed loop control system there. We've got an input, some sort of error detector, processor, driver controlling the output, and we've got some feedback here. There's an output sensor, and then that sends an output into the error detector here, and the error detector compares the input with the output, and depending on how close the input is to the output is to the required input, the processor can detect that and adjust the driver and the output device. It says explain the difference between a closed loop system and an open loop system, so it's just going on to the mark scheme. A closed loop system, you may have phrased it differently. A portion of the output signal is fed back to the input by the output sensor. We could say the output affects the input. In an open loop, there is no feedback signal. The output does not affect the input. On the second part here, it says the signal from the output sensor can either be added or subtracted from the input here. So you can either take a portion of this and add it to this, or you can subtract a portion of that from that there. And it asks you to describe the effect on the system if the signal from the output sensor is subtracted from the input. Well, that's the definition of negative feedback. Negative feedback is when the signal from the output sensor is subtracted from the input, or a portion of the signal from the output sensor is subtracted from the input. So all you need to know is the effect, the characteristics of negative feedback. And if you have negative feedback, if you remember, for negative feedback, the output doesn't saturate, so you can control the output to be at the required level. This one here, if you add a portion of the feedback, if you add a portion of the output to the input, that's positive feedback. And if you remember, a characteristic of positive feedback is the output saturates. So these two doesn't answer the question. It's just, I'm just saying that that's negative feedback, that's positive feedback. In answer to the question, you're looking at for the first one, for negative feedback, the output is just a non-saturated value, or you may say some constant value. You should make the point actually that it isn't saturated, whereas for the second one, if it's positive feedback, it's saturated. For the second one, it's the just a Schmitt trigger, so you're asked to calculate the switching levels. I'll let you work that one out yourself. It's giving you the answers that you're trying to get to. If you're not sure, you can ask a classmate or come and ask. Over onto the next page. Describe the output signal from the system. So what you have to recognise is that's a Schmitt trigger astable. When you take the output and you're feeding it back round here to a resistor and a capacitor, looks a little bit like a 555 timer circuit, doesn't it? But you've just got one resistor instead of the two. You've got to recognise that's a Schmitt trigger astable. So what you're looking at there is making the idea the output signal is going to be an astable. So just a little bit more information there. You're just going to get high and low continually repeated. I mean, you've said it's an astable, and that implies it's highs and lows, but you need to make the point that it is digital, high and low. In the mark scheme there, it refers to that as a square wave output. The idea of a square high and low is going to give you that would be a square wave output. It asks you to estimate the frequency of the output signal. Now, with a Schmitt trigger astable, if the output is high, what will happen is current's going to flow from the output there, like that, round there, flow through here and down there. So over time, if you sketch a time graph here, voltage, let's just add on here the switching levels of the Schmitt trigger, which you previously calculated 4 and 8. So this point here is the voltage across the capacitors fed into the input there of the Schmitt trigger. So what's going to happen is the Schmitt trigger voltage is going to start. There's the 12 volt point. This is the output voltage from the Schmitt trigger 12. So what will happen at this point here, if we call that point X, the voltage across the capacitor, that's going to start increasing there as the capacitor charges around there. And if you remember, it's going to draw a curve like that there. As soon as that voltage there exceeds 8, then you've exceeded the upper switching level of the Schmitt trigger. So the instant that happens, the voltage at the output is going to go down like that to 0 volts. Now as soon as that's 0 volts, what will happen is the capacitor will start discharging around that way, going down to low. So it starts to discharge down like that. But as soon as the voltage across the capacitor there, the voltage at the input of the Schmitts drops below 4, the astable goes back high again. And as soon as that happens, the capacitor is going to start charging again. So very similar to a 555 astable, you're constantly getting this charging and discharging. Now at that point there, the capacitor is discharging from 8 to 4. Now that is a third of the supply voltage, isn't it? The 4 is a third of 12. So if you remember on the data sheet for the exam, it tells you that the time it takes the capacitor to charge or discharge 50% is 0.9 RC. But can you remember from lesson that middle third takes the same amount of time as well? So the time to charge that middle third is also 0.69 RC. The time it takes to discharge that middle third is 0.69 RC, but also the time it takes to charge as well is 0.29 RC. So that total time there that covers the discharge and the charge, that covers the high and the low, is going to be 2 times that there. So the time period of this astable is 2 times 0.69 RC. Now that's the time period there. So if you look at the mark scheme there, the period of the output is 2 times 0.69 RC, which if you calculate is 1.38 times 10 to the minus 2 seconds, and then frequency is 1 over time period. So if you do 1 divided by that, you get 72.5 Hertz. So there's 2 marks in total available for that. So we've got an 8x8 multiplex dot matrix display showing you one of the LEDs lit, and it asks you state the signals that must be applied to the rows and columns to light only. So that's in bold, so you're going to have to think about that, only that LED. So that's the anode, so the anode there needs to be high, and if the anode's high, you're going to get current flowing along there, through there and down to there, as long as that's low. Now if we're making this end low, would that one light? Well, it might light if that was high, wouldn't it? If that was high, you'd get current flowing through there. So you have to make sure that's low, and similarly you're going to have to make sure all of these are low there. Now you've made that high in order for current to flow through there and down there, but you don't want this one to light. Remember, it's only that one. So this is going to have to be high, isn't it? If you make both ends of that high, you can't get a current flowing. So similarly, all of these are going to have to be high. So it does say state the signals that must be applied to the rows and columns to light only this LED. So your answer would be C5 must be low and R5 must be high. That's I think going to get you 2 marks. It's not exactly clear what the marks are allocated for in the mark scheme, but you must make the point that all the other columns must be high and all the other rows must be low in order to get excuse me, in order to get the 3 marks. Some of you may have given the value in hexadecimal. For example, with the rows, there's R0, so that's the least significant bit. So you could write 0, 0. It's perhaps best to put this 4 sort of split there. So you've got 4 zeros there, and then 0, 1, 0, 0. So if you were to write that in hexadecimal, that's 2, isn't it, in binary, and that's 0. So the rows would be that. Then if you do a similar thing there and just split that down the middle there, that's the least significant bit. So we need to excuse me, we need to flip that round. So 1, 1, 1, 1 slash 1, 0, 1, 1. So that's F. What's that? 8, 4, 2, 1. So that's 12, 13. Well, F is 15, so that would be D, wouldn't it? Nor X, D, F. So you may have written it like that, or you could have written it in binary or in words, but the essential point, as it makes clear on the mark scheme, is these points there, which you can check yourself in your own time. So okay, over to the next one. The LEDs have a forward voltage of 2.5 volts, maximum current of 15 amps, operates from a 5 volt power supply. So series resistors are needed to limit the current passing through the LEDs. State and explain whether these series resistors should be placed in the row leads or the column leads. I mean, if you just sort of do a little diagram there for a second, and just imagine a single LED with 0 volts there and 5 volts there, and you're thinking, okay, what protective resistor value would I need there? You could do a normal calculation, couldn't you? If you've got a forward voltage of 2.1 across there, that's going to leave 2.9 volts across there. So R equals V over I. So you'd have 2.9 volts there. That's the voltage across there, divided by 15 milliamps. And you could then calculate in ohms there, you could calculate what resistor value you needed. I'll leave that as an exercise for you to do if you like. Excuse me. Now if you use that resistor value there, that would limit the current through the LED to 15 milliamps. So you've got a choice. Should all the series resistors be in the row leads? Should each of these have a resistor on there? Or should they be in the column leads down the bottom here? Well, just imagine for a moment we put the resistor in the column there. Let's imagine we just made this one low here, and let's imagine we made all of these high there. And I mean, you can imagine that one as being high as well. So all of these high, that one low. It's going to light this one, isn't it? And this one, 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 and this one. Now, if you place the resistor there, you've limited the current in that resistor to 15 milliamps. So you'd have to divide that 15, sort of working backwards. If there's 15 flowing down here, and you've got 8 on, you'd have to divide that 15 by 8, which is approximately 2, isn't it? 15 divided by 8 is approximately 2. So you'd have 2 milliamps per each LED. That's not going to light the LED very much. Now, if you only had one LED on, if these were all zeros again, and you just had, say, that one high there, and that was the only one you had on, then that one would get the full 15. So the problem with the resistor on the column lead would be that the brightness of the LEDs would depend on how many you had on. If you had one on, it'd appear sort of full brightness, maximum brightness, but the more that you put on, the current would be shared more, and the dimmer the LEDs would appear. So that's not desirable, is it? Whereas if we just sort of ignore this over here now, if we go over to this first column, if each one, it's going to get a bit messy here, but just to sort of illustrate the point, if each one had its own protective resistor there, when you are multiplexing, you only have one column on at a time, don't you? And you try and scan the columns quickly enough that it appears permanently on. Now, let's say you only had this column on at a given moment in time. Let's just ignore this one now. Then, if you do make that high and make that low, that's going to limit the current to 15 milliamps, and that's 15 milliamps for that one LED. There's no sharing going on now. If that one was on, you'd get 15 milliamps limited there for that one LED. So you need to put them in the row leads, because the brightness then of the LEDs doesn't depend on how many are on. And if you look at the mark scheme there, that's the point it's trying to get. Resistors should be in the row leads. Now, I'm guessing that's going to be one mark out of the three. It hasn't given a breakdown. And it makes the point, look, that the current passing through the column leads would mean that the current would vary with per LED, that is, with the number of LEDs lit. But with the rows, it's saying that you only get one LED is ever lit per row. So there's, I think it's making the point there, there's no sharing going on. So it's saying if the resistors are put in the column leads, the brightness of the LEDs will vary with the number of LEDs lit. I think you would need to make the point as well that in the row leads, the brightness of the LED wouldn't vary with the number of LEDs on. Now going to the next question, the maximum current that each column driver must be able to switch. So what you'd have, in order to control whether this is high or low, you'd have a MOSFET acting as your driver at the bottom there, and if you turn that MOSFET on, you'll allow current to flow down here. Now if you've set the resistor here to limit the 15 milliamps current through each one of these, if all of them were lit, you'd have all those 15 milliamps adding up down here, and you've got 8 LEDs, so the maximum current that you could have if all were turned on would be 8 times 15, which is 120 milliamps. So that's the one mark for this question here. 5C and 5D, you could look at the mark scheme yourself. Sorry, 5D 1 and 2, explain why the eye can perceive a multiplexed display as a continual image. You do, for that one specifically, do need to refer to the image response time with an approximate value of about 60 meters per second. So what's that saying is, if you stimulate the eye and give it a quick flash of light and then nothing, if that's the actual stimulus to the eye, the sort of the cells in the eye will stay stimulated for 60 milliseconds. So if you repeat the external stimulus in a time of less than 60 milliseconds, then you'll re-stimulate the eye here, so that's just going to appear as one continuous stimulation to the eye. So it's just using that phrase, the image response time. It's just the response of the eye to the image. So you specifically need to make the point there. You may have worded it slightly differently, but you need to make that point there with that specific number. So if you think of this as the image here, if it's refreshed, it does say at a faster rate here, a faster rate than this. Now that's not actually a rate, is it? That's a time. So I would word it, if the image is refreshed in a shorter time than this, then the eye cannot see the changes, and so it contains continuous image. If you did want to put it into rates, you'd have to work that out as a frequency. I mean, often you could just quote an image response time of 50 milliseconds, about 50 or 60, somewhere around about there. Now, if you turn that into a frequency, 1 divided by time, if you do 1 divided by 50 milliseconds, that gives you 20 hertz. That's 20 times a second. So as long as you flash an image at a rate more than about 20 times a second, it'll appear continuous. So you could have framed your answer in terms of that. For the final question, estimate using a calculation the longest time there should be in switching from one column to the other in order for the observer to perceive a continuous image. State any assumptions you make. Well, let's say you've got that particular one LED there, and you're lighting this column, then this one, then this one, then this, and back to this again. This one would need to flash at least every 50 milliseconds. That's the image response time, or preferably less. So it's no good turning that on and then that one for 50 milliseconds and that for 50 milliseconds and that for 50 milliseconds, because that would be what, 1, 2, 3, 4, 5, 6, 7, 8. 8 times that would be what, 400 milliseconds. So approximately that would flash every 400 milliseconds, but it needs to flash at least every 50 milliseconds. So working backwards, you'd have to take 50 divided by 8, or even 60, somewhere around about there, and that's what it's got in the mark scheme there. If you assume an image response time, you'd have to quote what it is. It gives an example of 60, but somewhere around about there is acceptable. So that's the assumption that you have to state. And then since all 8 columns must be displayed in that time, you'd have to divide your answer by 8. And if you used a value of 60, that would be every 7.5 milliseconds. So if that was on for 7.5 and that 7.5 and that 7.5, then by the time you get back to there again, that will be just less than 50 or 60 milliseconds to repeat that. So it'd look to the eye as if it was continuous. Next question, you've got that vehicle there, and it can be potentially confusing because the options are the vehicle could stop, turn left, turn right, rotate anti-clockwise, move forwards and move backwards. Now you might think, hang on a minute, what's the difference between rotation and turning? Now the way to think about this, if we just go over to this rough diagram, obviously if this is the front here, if A and B both go forwards, then it's going to drive the vehicle forwards. If they both go backwards, it's going to drive the vehicle backwards. If B remains stationary but A goes forward, then if you think about the centre of sort of the vehicle like that, if B, I'm trying to keep B stationary here, if A goes forward, look what happens to the centre of the vehicle. It's actually moving forward as well, isn't it? So that would be turning right there. If A went forward at the same time as B went backwards, then that centre of that vehicle would stay there, and the machine would rotate on the spot. And that's what it means by the idea of rotation. Rotation is different to turning for this kind of vehicle. Rotation is where the centre of the vehicle stays at the same point, whereas turning left and right, that's when the centre of the vehicle doesn't stay at the same point. For example, turning right, the centre of the vehicle actually moves forward as well. So you just got to appreciate that in order to do that particular question. The rest of the question, I think if you check the mark scheme for this one, you will see that it makes sense. It's just getting used to the sort of the formatting of the question. I think if you check these ones as well on the mark scheme, there are multiple possible answers for this, and the mark scheme doesn't give them all. You may have your own knowledge that you've applied, but whoever's marking it will obviously check, do a little bit of research and check what you've said to see if it's correct. the standard kind of answers you can find in the support booklet. There's probably not too much I can add to the mark scheme really. It's just a case of learning the process. Describe the sequence of events if an interrupt request signal is received. If you look at the mark scheme, what you're looking for is the microcontroller completes the current operation and saves the current variables. I mean, it's specifically mentioned on the stack there. That is the region of memory where it saves them. I don't think that is necessary. You could just say saves the current variables. So that you do need both of those points. It completes the current operation and it does save the current variables. You do need for the second mark to say jumps to the interrupt service routine, not ISR. You have to specifically say interrupt service routine, and then you do need both of these points there, that it returns the variables from the stack or from memory, and then you do need to say it continues with the previous program. Polling is another method you could have used, so 1 mark for polling, and you need to just say what polling is, repeatedly checking the inputs to detect a change. And then in terms of comparing an ANN with traditional machines, pretty standard kind of thing really. It's all there in the mark scheme. The only thing that you do need to be aware of is serial processing is relatively slow. A lot of you thought that ANNs were relatively slow. I think the simulation you saw in lesson was relatively slow because it had to constantly adjust the weightings. But that was the process of training the ANN. I mean, even then, it might not. Don't think that training a real ANN would be as slow as the simulation we saw in class. The syllabus point that needs to be emphasised here is if you're doing an operation 1 by 1 by 1, line of code by code by code, it's going to be quite slow. Whereas for an artificial neural network, when it's actually being trained, it's parallel processing. So that makes it a lot faster because you're not just doing sort of one calculation at a time. You've got multiple sort of calculations going on simultaneously. That's the end of the video then. I hope you found that useful. If you do have any questions at all, please ask me in lesson or come and see me. The more practice you do, the better you'll get, and the more care that you take with these mark schemes, and the more you reflect on your own way of learning, then the better you will do. So good luck with the next one.